Okay, next up we have Dr. Larg Weiland from PDF Solutions, and Dr. Weiland is going to share some of his insight to OASIS and what he has found, and dealing with some huge data sets and learned a lot about OASIS. Some members have expressed an interest in some sort of OASIS to OA to converter, and if you have an interest in that and are willing to participate, then we would have the makings of a working group, and that can occur within open access or within open standards. So it would depend on how that is defined.
Okay, let's get started. So as Marshall pointed out, so let's have a little deeper look into the OASIS format. Just a quick agenda. So I give a quick introduction and motivation why you want to look into file formats, and kind of a historical overview of what formats exist and still used, like a brief history about GDS2 and a brief looking inside. Then the same thing for OASIS. I go a little deeper, and then I'm looking especially at the aspect of OASIS, why it does such a good job in file reduction, and how is it done. I will comparison between OASIS and GDS in terms of compaction rates, then some notes about today's EDA tools, that some create good OASIS and some create very bad OASIS, and then from my point of view, some notes about problems with OASIS in terms of the file format, and what it takes to create an OASIS writer and reader, as Marshall pointed out, if there is such a thing as a workgroup to create an OASIS reader and writer. And I draw some conclusions at the end. So there's quite a lot of exchange formats. Noteworthy are probably CIF, GDS2, OASIS. So CIF is something which is called the Caltech Intermediate Format. It's from 1977. It's still used. It's ASCII format. It's easy to write, easy to generate. It's probably good for small things. If you want to try something out, simply write an OASIS, a CIF format, and read it in. So I see it, especially for universities, a lot, and even I use it sometimes because it's just easier to generate something automatically. Then came GDS2, kind of in the 78 from Calma. It's called the Graphic Database System. There are these days some limits with it, or I mean there are some limits because it uses 4-byte signed integers, which if you have a 1 nanometer resolution or DPUs, it adds up to plus minus 2 meters. I mean, you will say, okay, 2 meters is big enough. We have our wafer size are way less than this, and reticle for sure less than 2 meters. But anyway, if you go down with the resolution, which you have to if you go to the latest technology nodes, then it's getting tight there. Another thing with GDS2 is many objects in GDS2 are officially limited. So the original spec says there is, for instance, you can only use 63 layers. But in reality, all EDA companies support at least more than 3. We look later on a little deeper into that limitation. So what I'm saying with that is it depends on the tool, how this is interpreted, how strictly these limitations are interpreted or not. Then OASIS is the standard came 2001 and version 1.0 in 2004. And the intent was really to reduce the file size. And they used various techniques, and we go into detail about these techniques like grouping objects by the same layer, or having polygon points stored relative to the previous point instead of point by point, like special rectangles and trapezoid objects, then optimize the array structures like random distribution of arrays instead of just X, Y, or row column arrays. One of the powerful things is like variable length of numeric values, so you don't have like a 4-bit or 8-bit integer. No, it's dynamic. You can have an n-bit integer, which of course by itself causes other problems. So again, what I mentioned, GDS2 has limits, and many are up for interpretation, like all these artificial limits in terms of number of things. What I see is adoption of OASIS is unfortunately very slow, but I see it more and more, especially in newer technologies, because by default, these files are just exploding. So why would you care about the details of the data format? So why do we need to listen to this presentation? At least for me, I write a lot of point tools to directly read and write OASIS, and they might be very useful for you or not. For me, they are. And examples are, we like to check, for instance, did I use all the layer data types correctly, or is there anything in the file which is not supposed to be there? Are IPP tags there or not? I might want to extract some certain attributes or properties of a GDS or OASIS files. I want to verify that DPU settings are correct. Maybe swap, replace, or delete cells within a GDS or OASIS files, extract cells. So there are many useful applications where it might be necessary to write a little point tool which can read and write an OASIS file. And a second motivation, of course, if you're interested in having an OASIS reader and writer or open access, then there might be the option to create or in discussion that we create a working group at SI2. So GDS2, let's have a brief look at how this format works or how it's structured. So what you see here is the BNF, so it's called the Backus-Nauer form. It's a description language for context-free grammars, and it's very easy to read. And let me just read the first line here. So GDS2 file is something which has a header, a begin lib, some optional parameters, which are all these in square brackets, and then one or more structures and an end lib. So I think everyone can read this line and kind of understand, okay, this is how it might work. And then you can go deeper. What is a structure? A structure is something which has a begin string, a string name, and then some optional parameters and a number of elements and an end structure command. And then an element itself is something which can be a boundary path, aref, sref, text, node, and an end element. And so with the syntax, it's really easy to understand. For instance, if we look at the element of what a text element is, so text is something which has, again, some optional parameters, then for sure a layer, a text type, then another few optional parameters, a transformation, and the XY coordinate, and the actual string. So if you are interested in how the full spec of GDS2 is not much longer than this. Of course, for each individual record, you have some more definitions in there, and in total you have 60 different records. Another thing about GDS2, this has 6 data types. So there's a bit arrays, there's 2-byte signed integer, 4-byte signed integers, 4-byte reals, 8-byte reals, and ASCII strings. As I mentioned, it has 60 records, and a record is simply something which, like a begin string is a record. It has a record ID, followed by, so first it starts with the length of the record, then the record number, the data type, and then your raw data. That's the structure of every record, not any of these 60 records. So as an example, the begin structure record, so the length is 000C, meaning 11 character, 12, sorry, followed by the record number, which is 06. The data type is 06, which is the data type for a string, and then comes the raw data, so 45, 58, 41, 40, and so forth. That's just your raw data of that string. So it's fairly simple. So this format is very easy to parse. You can use something like YAC, if you're familiar with this, with a custom lexer. So this gives you the ability to write it in a very readable way, to write a parser for GDS. Of course, you can use any other method to parse these files. Limitations, as I mentioned, is it's a 4-byte signed integer, meaning 32 bits, which is in 1 nanometer resolution. It's plus minus 2 meters. The layer data types, theoretically, they are 2-byte signed integers, so 32,768, but artificially limited to 63. Again, this format is out of the 70s, so maybe there was a reason why they did this. And some tools, they just can't read all their 32,000 layers. Same artificial limitation with cell names. They're limited to 32 characters. Arrays, is a hard limit, so they are at 32,768 of number of rows and columns. The bigger problem is the length of a record is a 2-byte length limitation. So meaning you cannot have unlimited number of polygon points in there, because at some point your length record, your 2-byte of your length is not enough. There's some curious thing about GDS. So if you always wondered, you added one polygon and the file size didn't change. And this is because they require the file to be in multiple of 2048. So they've still essentially at the end of the file, there is a 0 padding in there until they hit the 2048 multiple of the file size. There is no built-in compression in GDS, but what you can always do, and everyone is doing probably, is doing a zip or bzip2 or any other compression onto your file, and most tools can read natively these zipped files without uncompressing them before, because whether you open the file directly or open a pipe in Unix doesn't really matter. So now let's look at OASIS. Again, here the BNF. Interesting enough, they have a BNF in the OASIS documentation. And a funny side note is you can't use actually a grammar to parse the file. So you can't use YAC, for instance, to parse OASIS. It's impossible. I'll tell you why later in a moment. So let's look at the first line again. So an OASIS file is something which has a starting byte, they call it magic bytes. It's just an identifier which clearly says this is OASIS. And then start record, and then some optional things, meaning it can come, so there's an OR essentially, either it comes a C block, a pad, a property, a cell, a name, and then that's it. And multiple of these. And here starts the problem with OASIS. The file is very loosely defined, so it's OR. So whether you have, for instance, this name record, which is, for instance, a cell name text string. So name is kind of a layout, as a table of strings, which is one of the methods of compression of that file. So these string tables can be at the beginning of the file, according to that grammar, or they can be at the end of the file, or they can be in the middle of the file, or they can be distributed within the file. So there's no real, oh, this has to come at the beginning. So it's open for interpretation. Whatever you want to do, you can do. It's the second problem, for instance, look at something like a text element. So text has an ID, which is, in this case, is 19, and that comes this kind of oddly thing, which is a text info byte, and this is valid for any other record as well. It works the same way. And the text info byte tells you, so it's 1 byte, which has a couple of bits, which say, oh, if this bit is set, like if the X bit is set in here, then comes an X, the definition of X. If it's not set, then take it from the previous record. So essentially, you have to make a decision once you determine, oh, there's a text element I have to read. You have to interpret this text info byte. You take it apart, and you know what's coming after that. So it essentially gives you the info what to parse next. As I mentioned before, it's a pretty complex grammar, and it's very loosely defined, like what I mentioned with string tables, that they can come anywhere in the file. I didn't find a way of being able to parse it with YAC. there is no way because of this text info byte. There is essentially, if you return a token, you cannot do operations on a token in terms of ending it with some bit mask and say, okay, this is the following grammar in case this bit is set. So you have to have some other ways of parsing this file. I only talk about YAC because I'm just a big fan of YAC parsers because they're easy to read. So that's just my thing. Anyway, we talked about compaction methods. So OASIS uses quite a lot of ways of compacting the file. One is built-in compression. They call it a C block, meaning any kind of record can be compressed using this zlib library, and we just put in a file. And I think this is a little bit awkward that they have this in-file compression, because I think at the end, if I compress the entire file, that should be enough. Because the effort of parsing such a file where you have uncompressed data stream and then suddenly you have a compressed data stream, it's kind of really awkward, and it's relatively complex to implement if you need to deal with two different streams, input streams. They have dynamic data types, meaning there's not a 4-bit integer, there is an n-bit integer. They have so-called deltas, and I will give you more details about each of these, like these string lookup tables. They have something like they call modal variables, repetitions, which is very powerful. And they have quite a lot of more native geometric shapes other than polygons, paths, and rectangles, like trapezoids, C-trapezoids, and so forth. Here. Okay. So, as I said, the built-in compression is just using the zlib RFC 1951 compliant. If you want to implement it yourself, you use the zlib, you have to get to the RFC 1951. You need some special flags. If not, so if you take the zlib as is and try to uncompress it, it doesn't work. Anyway, so the fact with that is, since they use internal compression, and if you run then at the end a file compression on it, it kind of makes it obsolete, because a compressed file you can't really compress a compressed file very well. So it's kind of worthless. Data types, as I mentioned, these dynamic data types, and the way this works, as you see, for instance, the number 127 is a single byte, and they take the first bit, which decides whether you have some following bytes. Like if the first bit is 0, then that's it. So this is why you have essentially 127, and then if you want to have 128, you need 2 bytes for that. The first bit in this first byte is 1, meaning there's a following byte coming. So this is how they kind of code the unlimited integers, or they have it also for reals and others. The deltas is just a smart way of, instead of saving every point with an XY coordinate, they have different types of deltas where they can do just horizontal, vertical offsets, or offsets in all directions, or the G deltas, which are kind of really in any direction. Another form of compression is the string tables. They use this, for instance, to store cell names, meaning if you have repeating cell names, it's easier to store the cell name in a table and then have just an integer or a long value to look up the cell name in a table. That compresses it quite a bit. And they have this for cell names, layer names, properties, and of course text labels. Then modal variables, that's essentially a set of parameters can be stored. So when you read something, you always store what you read in the modal variable, and then if it doesn't change, you don't need to redefine it. Meaning, for instance, if you stream out all your metal 1 first, then essentially you only define the layer metal 1 once and the data type for all the objects, and then you don't need to repeat this information in the file, which is really clever. Another thing is repetitions. That can potentially achieve a huge compression. So where you have in these days EDA tools, we have arrays or mosaics, and they have rows and columns. So these are represented in the OASIS file as type 1, 2, and 3. But beyond that, OASIS has other array types like diagonal arrays, if you look at type 9, or any kind of random distribution of an object like type 10 and 11. The problem with this is that in order to generate an object of type 9 or anything else than 1, 2, and 3, you have to spend some time in really looking at the layout and seeing, oh, how are my instances, for instance, distributed, or my rectangles? Which of the types do they represent? So it's kind of a trade-off with CPU time and the amount of compression you will achieve. Here's just some comparison between compressed or between files, same data, either once as GDS2 and once as OASIS. And in the sources, you see there's lots of papers written about how good OASIS is, and you will find all these charts in these papers, and if you have time, read them. It's quite interesting. But for instance, there was one paper from 2003 where they determined they can reach 5 to 20x compression. So if you have the raw GDS compared to all variations, GDS plus zip, plus different kinds of zipping tools, or then OASIS and OASIS zipped and so forth, they reached up to a compression of 20. A newer paper from 2008 was reaching between 10 and 50 compression. So, for instance, I was just dealing with a file which I got, which is latest technology node, and the file size was about 6 gigabytes OASIS, and if you would change that into GDS2, convert it, it's 300 gigabytes. Just some fun facts out of this file. It has about 6 to the power 6 cells and 2 billion instance placements in there. So not every EDA tool is equal. What do I mean with that? I was looking, just because I was writing my own OASIS parser, I was trying to create some test cases, and I was just writing out OASIS from various different EDA tools. And I was wondering, why are they not using certain constructs like repetition types 3, 4, 5, 6, 7, 8, 9? So I was playing essentially around. And one of the problems, what I mentioned, is that many OASIS constructs are not a native object in an EDA tool. So it requires essentially CPU time to find compression, to see how, for instance, instance placements are distributed, and then combine them into some type of repetition. And there's a clear trade-off between speed, of course, and the compaction level you can achieve. And depending on how much time you want to spend, you can really reach high compaction. So, for instance, I was doing a little test to see what EDA tools are doing, and I was just placing 4 instances of a single rectangle in kind of a random distribution, and I was expecting that they generate 4 repetition. And what I found that tool A was essentially the file size of that of these 4 instances with a single rectangle was 357 bytes. So that was my reference, and then I was using tool B, and suddenly I got 100% bigger file, and tool C was 115%, and GDS was, of course, 2048. But if I look at the GDS, if I do a binary dump, most of the content of the GDS was zeros because they zero padding to 2048. In reality, it was actually smaller than the most compact OASIS files. But that's just in this little case. But don't take this as GDS is not compact. But what I'm saying here is that the results are different because tool A and C was using repetition type 10. Tool B was not using any kind of repetition. It was just dumping single instances out. And A was smarter and used also other forms of repetition. So it highly depends on the EDA tool, what they are doing with it, and how much time they are willing to spend of really compacting a file. So problems, just to summarize some problems I see. So I think the grammar is a little too flexible in terms of, especially string tables, that they can be at the beginning, at the end. So, for instance, a string table is for sure at the end good when we talk about writing a file, but it would be way better if it's in the beginning of the file if you're reading a file, because you want to get first of all your cell names and text strings. It just makes it easier if you have them before you actually get the data. Then comes a really awkward thing that besides the fact that you can have a string table, you can have also local strings, meaning you mix suddenly lookup tables with locally defined. And that makes it really complex in terms of internal data structures. So you might need to maintain two types of tables for local storage, for these tables, and so forth. Then I think the C block compression is kind of unnecessary. It just makes it more complex if you're having to deal with two streams, one compressed, one uncompressed, and instead of having just everything uncompressed and then use file compression, it would just make it easier. Dynamic data types, as great as they are, they of course can cause problems with older hardware. If you think of if there's still 32-bit hardware out there, how do they interpret an 8-byte integer or a 12-byte integer, or however big this thing might be? So that might be a big problem. The files can't be really parsed without interpreting every single byte, and that was the way I started, essentially writing an empty parser, which does nothing else than going over every byte of the file without doing anything, just to make sure it can read the file without any error. And really, without looking at every single byte, you don't have a chance of parsing this file. Not as in GDS, where you have a record length record indicator, and you can jump over certain things. You don't need to read them in. The only thing in OASIS where you can do this is with the C block, where you say this compressed block, because it has at the beginning a length of the block in there, so you could jump over it, but then you don't know what's in there. There's clearly no definition of any kind of limitation in OASIS in terms of how many layers, how many data types, so that's up for interpretation by the EDA tools. I mean, I think that's okay. And another thing is that many constructs, I think this comes on the next slide, so sorry. So creating an OASIS reader and writer. So what does it take? I think it's not a simple task, because it needs to be 100% compliant with the specification, meaning it needs to deal with all cases. And in order to achieve that, you need a vast amount of test cases, and it's really hard to create test cases if you have tools which don't really use any native OASIS objects. So meaning you need to write a writer first to create test cases for a reader. Then keep in mind, like my example I was giving you with the 6 gigabyte file I had to deal with, there were 2 billion instances. So if you use a data structure to store your instances, for instance, and you use a single pointer in there, an 8-bit pointer to something, let's say to the string or to the master of this instance, this alone is already 15 gig of memory. So if you deal with 9 billion instances, 2 billion instances, sorry. So your memory kind of explodes pretty fast by just not being clever about the data structures you're using. So you might want to double think. And maybe high-level languages like if you would use C++, because can be very wasteful sometimes in class definitions, where if you write it in maybe more closer to assembler in C, you have finer control over really where your memory goes. Maybe there's something like multi-threading, which could potentially reduce time, but it's harder to implement, especially for that file, without having any kind of indexing, so that you can jump over things you're not interested in. You would need to have a single pass of reading this file first to make your index table, and that kind of dynamically parse multi-threaded. For the writer, there's clearly a big trade-off between the writing speed and the compaction level you can achieve. So the more time you spend to find repetitions, for instance, the more compact your file will get. It would be for sure nice to have kind of a slider, and I've seen this with one tool where you have a slider which says this is the compaction level you want to achieve, and so it just takes longer, so you are aware of, okay, I trade off speed versus compaction level, but I'm in charge of it. And of course, if you write a writer, you need to test it against any major EDA tool, whether this is compatible or not. The conclusion is, so OASIS for sure has, or has the potential to be a super compact file format. There's no question about it. Adoption is slow, and it's for certain technology nodes it's not necessary because files are not so big, so it really doesn't matter whether you use OASIS or GDS2. But for bleeding edge technology nodes, I see more and more coming because files are just simply, I mean, if you deal with a 300 gigabyte GDS file, it's just too big. It's for sure not an easy task to create a good reader and writer. Unfortunately, the native EDA support for many compaction constructs are not there. For instance, there are just no constructs in any EDA tool for orthogonal, non-orthogonal arrays. So it would be really a cool thing if EDA companies would go there and look at different ways of storing. Why don't I get an option for storing diagonal arrays or things like native OASIS constructs? That would make it, first of all, way easier to write super compact files, and honestly, it would also save storage or memory on the EDA tool itself. Increase CPU time to create good compaction level, that's what I mentioned. So, and some constructs are open for interpretation. I mean, I think that's always something, even for GDS, so it's not different for OASIS. And then there's no simple parser to just extract certain features, like my little use case where I wanted to extract some IPP text. So you always need to almost implement a full-blown specification to do anything with an OASIS file, since you have to interpret every single bit and byte in that file. And that concludes my presentation. Any questions?
Larg, this is Ted Paone. Do you know about the ability if you're using strict mode, that you can have the cell start offset in your cell name table?
Yes, but it highly depends. So since I'm dealing with, so I'm getting files, so I'm not really writing these files. I'm getting these on various clients, right? So I have to kind of take what I get. And so it doesn't really help me that and most of these don't use any strict mode. So I thought I was running over files which have the table in the front and at the end.
Mm-hmm. And they weren't using the offsets.
Nope.
Okay.
I mean, I definitely would like to have any kind of string table at the beginning of the file. It makes it just easier.